Is this on? Yeah, that's on. Good. Howdy. It's always a pleasure to be here. I regularly visit A&M, and I have lots of colleagues to talk to. It's always a pleasure to be here. Like Casey said, I got this laser pointer, I think 6 years ago or something. I gave a colloquium here. Of course, this building didn't exist, and I wasn't a tenured either. So it's a big difference. Glad to be back. So today, I would like to tell you about generally what we can learn and also what have been learning using microwave background. Then this is a colloquium, so I understand that this talk should be very pedagogical, and I hope I will achieve that goal. So let me start. So what we do here is a cosmology, and what do we do here? So basically, cosmology asks questions about the whole universe. How old is it? How big is it? What shape does it take? What is it made of? And how did it begin? Now, all these are very, very old questions. Many ancient people pose exactly the same questions. Now, of course, we're doing things in a slightly different way. Namely, we actually now can observe, for example, the physical condition of the universe when it was very young, directly, in the form of a cosmic micro background. And that made this whole cosmology science a testable science. So that's a big breakthrough. So basically, I'll try to convince you that this is the case, and then we have made very good progress as to what the answers to these questions are. Okay? So what is cosmic micro background? It is the first light of the Big Bang. So universe was born, very hot, expanded, cooled. But the light that was there when universe was born didn't go anywhere. It's still with us. We don't see them like the sunlight because these photons are very cold. Universe size doubles, the temperature halves. So let me see if I can show you that kind of evolution of universe using a movie here. So this movie isn't a very scientific simulation or anything. It's in fact almost like a cartoon that I took from IMAX movie called Cosmic Voyage. Now you can rent the DVD of this. This is a fantastic scientific story that they created. Although this is a cartoonish picture, it's surprisingly highly accurate. So let me just show you, and you probably appreciate sort of the power of this kind of visualization. So let me do it now. I need to dim the light, but I will turn the light back again after this movie. So don't fall asleep just yet. Later, yeah. There you go. So the universe was born, and it's very hot, expanding very fast. But as the universe expanded, it slowed down. The expansion slows down, and then also universe keeps cooling down. Like I said, size of the universe doubled, temperature halved. But at a certain point, the universe became transparent for the reasons I will tell you later. You see, now universe became transparent. Temperature of the universe at this time is about 3,000 kelvins. Then temperature continues to fall. But the one thing that you want to remember for the rest of my talk is that you see how lumpy it is. When the universe was born, they didn't really give rise to very homogeneous thing. I mean, you always have this lumpiness. It is this lumpiness that then collides with each other. This is another important point. In the universe we live in, small things form first, and then they merge, and then create bigger and bigger and bigger things. These are not yet galaxies. These are just clumps of matter. And temperature of the universe at this time is still hundreds of kelvins. So we're not there yet. Today's temperature of the cosmic micro background is 2.7 kelvins. So this is still pretty hot. But then you see that bigger and bigger things are formed continuously. Then maybe some of them will become galaxies. The temperature continues to fall. And then eventually you see things like Milky Way. Yeah, you see that it's very blue, so temperature is cold. And then you see Milky Ways and Andromeda. At this point, it's really cartoon, so let me just move on. But now you got the point, right? This is a highly accurate visualization of what was really going on in the early universe. Now, this light that you saw at the beginning of the movie, they're still with us. If you ask me how many photons from the Big Bang you have per cubic centimeter, it's 410. You have 410 photons per cubic centimeter from the Big Bang, right there. Incidentally, you also have 360 neutrinos from the Big Bang, right here, per cubic centimeter. So they are still with us. These are very, very abundant particles in the universe. Another way of understanding what cosmic macro background looks like on the sky is this. So you have night sky in optical. If you go to the southern sky, this is the kind of sky you see. But then if you have, so your eyes are sensitive to visual wavelength like this, 0.4 micron to 0.8 microns or so. But cosmic macro background is way too cold for you to see in this kind of wavelength. It's radio wavelength. So if somehow you're given eyeglasses that are tuned to microwaves, say millimeter wavelength, then this is what you see. In fact, it doesn't even matter if it's night or day. This is the brightest thing on the sky. It's a millimeter, many, many photons. And then temperature of this was determined accurately by COBE satellite. There is a spectrometer here, very cold, absolutely calibrated spectrometer here that will measure the temperature of the sky down to this accuracy. Now, then, but the most important thing is, of course, temperature, right? So when we talk about temperature, what kind of spectrum are we talking about? That's will be the second question. And the answer to this question is this. It's a remarkable, perfect black body spectrum. And then deviation from this black body hasn't been found. In fact, this black body spectrum is so accurate that you cannot create this precision of the black body in the lab yet. But Big Bang knew how to do it. So this is the most precise black body in nature we have in the whole universe. And you see that, so here's the Phi-RAS instrument, that's the spectrometer, and it gave us lots of data points like this. There are a whole bunch of ground-based experiments here. Then this magenta line is the Planckian spectrum, black body spectrum with 4 Kelvin temperature. The yellow that you can't see here very well is a 2 Kelvin, and the green is 2.725. So clearly this fits data most. Now, why this is interesting? If you think about it, okay, it's not that hard. It's not that easy to create a black body in the lab. Why is that? Because we can't really have perfect thermal equilibrium in the lab in high precision. So when you have thermal equilibrium between matter and radiation, this is what you get out. What that means is, remember that these are photons from the past. In the past, universe was just like a fireball, literally fireball, with matter and radiation in thermal equilibrium. So this single observation proves that there was a period of hot and dense phase of the universe. And we normally call that a Big Bang. So Big Bang is the period where the universe was very hot and very dense. And this proves the existence of that. So the existence of that is no question. This, you cannot explain this otherwise. Now, how was cosmic micro background radiation created? So when the universe was hot, it was a hot soup made of protons, electrons, helium nuclei, photons and neutrinos, dark matter also. But dark matter, which I'll talk a little bit more about later, doesn't do much because this dark matter, being dark, doesn't really interact well with photons or ordinary matter. They do so very, very weakly. So they don't really do much, except they provide a gravitational potential. Because as we measured it, the density of the dark matter, mass density of the dark matter, is 5 times as much as mass density in ordinary matter, such as helium and hydrogen. That's what the universe was before, and then here is universe as a soup. So this is before universe cooled down sufficiently so that electrons are combined with protons to form neutral hydrogen. So here, temperature was too hot to keep electrons inside of neutral atoms. By the way, is this microphone howling? I hear low level noise. Is that okay? Maybe I should. Yeah. It depends on the location. Okay. All right. What should I do? Is it okay? Sort of. This works. Yeah, that's right. All right. So, well, okay. Oh, it's better now. All right. Can you hear me well? Yeah. Okay, good. All right. So what happens here is that electrons are all stripped out of the neutral atoms. So you have just protons, helium nuclei, and free electrons. Electrons are very efficient at scattering photons through Thomson scattering. So photons can't travel freely. Mean free path of the photon is much, much smaller than the size of the universe, or horizon size of the universe at this time. So the universe is very opaque. Optical depth is too large for you to see anything this period. But once temperature of the universe falls below 3,000 kelvins, then all these electrons, most of them, are combined with protons to form neutral hydrogen. A little bit earlier, electrons are also combined with helium nuclei to form neutral helium. And then neutral hydrogens or neutral helium are not as efficient at scattering photons as free electrons. So photons mostly just go straight. After this, photons go straight, then we can see them. So what that means is when we observe microwave background on the sky, this is the period that we are seeing. So we have a snapshot, a photograph, literally, in the literal meaning, a photograph of the universe when the universe was 3,000 kelvins. Not quite as early as the beginning of the universe itself, but it's pretty early because age of the universe at this point is only 380,000 years. Current universe is 13.7 billion years. So this is basically the infant stage of the universe. So we call this period when the neutral atoms are formed, epoch of recombination, and also when we call the epoch at which photons are last scattered, and then after which they propagate freely, decoupling epoch. So basically, we are seeing photon from the decoupling epoch. Now, let me show another movie again to summarize what we just learned now. Namely, how does cosmic microwave background look on the sky? And also, I'm going to show you some of the real data from now. But to appreciate what you're really seeing, this kind of movie I'm going to show you now helps. So let me just do that. So this is Milky Way. And then let's put ourselves into the place we belong to, which is 8 kilopascal away from the center. So that's us. Then put them back into the location where we belong. Now, notice that this is a sky we see. So we are inside of a sphere now. This is a sphere that we observe on the sky. We are surrounded 380 degrees, surrounded by the sky we see. But we want to somehow project this onto the two-dimensional surface, like screen, computer screen here. So let's expand this. This is so-called galactic coordinate. So you have the, so we are now at the center of the sphere. Then this is how we see the sky, 380 degrees, but projected on the flat surface, like screen here. Galactic center is here. These are Magellanic clouds. This is galactic coordinate, but in the usual coordinate, celestial coordinate you're familiar with, we can observe only this part of the sky from the Texas. And you have to go to the southern hemisphere to see this part of the sky. That's why we don't see imaginary cloud here. So this is the visible part of the spectrum that we're familiar with. But then we go to the longer and longer wavelengths. So this is near-infrared background, near-infrared light. And you start seeing this so-called zodiacal light. That's interplanetary dust heated by sun and radiating in infrared, which you don't see in optical, but you see it in infrared. In fact, this is a big, annoying light for astronomers working in the infrared. That's far infrared. Dust is emitting like crazy here. Then you go to sublimimeter. Things are more structured. You see cold molecular clouds and so forth. But still, you see galaxy. This is basically our Milky Way, seen in a different wavelength. But by the time you go to microwave, this is what you see. See? This is the light from the Big Bang. But that's not the end of it. As I told you, universe was born, it's got lots of lumpiness in it. And that has to be imprinted in the microwave background too. This is completely homogeneous. It's at 2.7 kelvins, but if you increase sensitivity of your instrument by 100,000 times, you see this. So this is the lumpiness that was imprinted right after the universe was born. And it is this that tells us a lot about what the universe is doing. Its age, composition, and then also the physics of the very, very early universe that we won't have access to otherwise. So that's why cosmic micro background revolutionized our understanding of the universe. Who discovered this first? We talked about Kobe. Kobe also, in addition to this spectrograph at the center, Kobe also had a few other instruments called a differential microwave radiometer, 3 of them, working at 3 different wavelengths. What they do, they don't measure absolute spectrum of the sky, but they measure differences of the temperatures on the sky. Now, what you see here is basically 100 microkelvin. But the mean temperature is 2 kelvins. So you're seeing these only small variations across the sky. Important thing is, cosmic micro background isn't really isotropic. It is, in fact, anisotropic. This is coming from the lumpiness in the very early universe. So, that's cosmic micro background then. And then that's where the temperature of the universe is 3,000 kelvins. We're observing it from here. And then because if you see more distant things, you're looking more into the past. So you're looking back in time. So what that means is cosmic micro background is the oldest light we can possibly see by electromagnetic waves, which means cosmic micro background is the farthest light we can see by electromagnetic waves. And that has an interesting implication, because if we can measure distance to this epoch, then you divide that by speed of light, and you get age of the universe. Normally, astronomers measure age of the universe by measuring age of the stars. But of course, it takes some time for stars to form before the universe was born. So that kind of measurement is always inaccurate, but with this measurement, which is completely different, we rely on distance rather than measuring age. Then dividing distance by speed of light, you get age. Then you will get highly precise measurement of age, 13.7 plus minus 0.1 billion years. So that's how we got the age. All right, so let me talk about WMAP. This is the sort of successor of Kobe. It's a microwave, the Wilkinson microwave anisotropy probe. It was launched in 2001, and then has been continuously taking data up until last year. And then last year, let's see, last year, 2 years ago? I think last year. Around August, WMAP stopped taking data and left orbit. So WMAP mission is finished. WMAP is not circling around Earth. It's actually at Lagrange 2 point of the Earth Sun system. So what that means is, so Lagrange 2 point is a million miles from Earth. This is a good place because it's a saddle point in the potential of the Sun and Earth. So it's a good place to stay, linger for extended period of time. And what's nice about it is that there's a Sun here, and there's Earth here, and Moon circling around it, all of which are very strong microwave emitter. But at Lagrange 2 point, you can leave all of them behind you, behind the solar panel. So you can continuously observe the sky, 100% efficiency. You don't have to worry about WMAP looking into the Sun or Earth or Moon, which are all strong microwave emitter. That's why we went up there. And now there are two more satellites in here. One is Planck, which is this third generation microwave background experiment, and the Herschel, which is a sublimator telescope, astronomical telescope. How does WMAP work? It works like this. So we have two mirrors, about 1.5 meters, and then we look at two locations on the sky simultaneously, 140 degrees apart. We take light, then we take difference. Now, when the response of each detector is the same, then you cancel out the term that's constant across the sky, namely 2.7 Kelvin. You cancel them out. What's left is the fluctuation part. What's left is this anisotropy. And it's good that doing this way, because otherwise, if you have to subtract this 2.7 Kelvin by yourself, by absolutely calibrating to the instrument, the cancellation has to be perfect at the 1 part in millionth level. That's very hard. So it's rather easier to do this way, differential measurement. It worked for COBE, so we use it for WMAP as well. Unlike Planck, which is the third generation, which is already up there, and in fact already stopped taking data, we are not cryogenic experiment. We just radiatively cool, which sounds like a bad idea. It's rather warm here, 90 kelvins, but we didn't need to have any cryogenic component, which NASA loved. NASA didn't want to take any risk, so so we did that way. So we didn't. Our instruments are not as sensitive as one might have wished, but just good enough to deliver significant science. So we're pretty happy with that. But added bonus that we don't cool by cryogenic instrument is that lifetime of WMAP is basically indefinite. So what limits lifetime of WMAP? It actually what's limiting lifetime is the fuel. Lagrange 2 point is not the bottom of the potential well. It's on the top of the hill. It's a saddle point. If you don't do anything, it will slowly drift away from the L2. It's a nice spot in some sense, because if you stop working, you slowly drift away. This is a place where things are always kept clean. You have to do the maneuver to stay in L2. So now, but after we learned that the Planck is working well, Planck is 10 times more sensitive, we decided to end the mission, leave the L2, and then WMAP is now circling around Sun at 1.08 AU. So it's like a little farther away from the Earth, and it became a planet. Basically, it's circling on the Sun happily. So what did COBE did? So COBE measured the map. COBE created the map of the sky in this angular resolution, 7 degrees. WMAP has 35 times better resolution. It's about 10 arcminutes. Now, what does that buy you? Right, I'll tell you that. But before I tell you that, let me just tell you that. So this is the WMAP 7-year science team. We're about 20 people doing scientific analysis. Chuck Bennett in the Johns Hopkins University is the PI of this mission. And then we published a set of papers for 7-year data analysis, and I'll be focused on this cosmological interpretation paper. Now, here is the sort of causing pie chart, 7-year. So we have this strange cosmological standard model where helium and hydrogen, the stuff we know, occupies only 4.6% of the energy density of the universe. Dark matter, so there is matter. Matter occupies about 27%. It turns out that the ordinary matter occupies only 4.6%. Rest is something we don't quite know, dark matter. Probably some subatomic particles that we haven't yet found. Maybe we'll soon find them in LHC, who knows. And the rest is not even matter, it's dark energy. We call it dark energy and distinguish from it, from matter, by noticing that this stuff actually has enormous amount of pressure with wrong sign, namely minus sign. So this one has a large negative pressure, which cannot be the case for matter, ordinary matter or dark matter. Matter, by definition, has negligible pressure. Dark energy, by definition, has large, enormous negative pressure. That's how we distinguish the thing. Of course, Nick Sanchez here was a key player discovering dark energy using type 9 supernovae. Probably many of you heard his Colloquium. It's a beautiful story. It's got a Nobel Prize, so it's really there, apparently. And then, now WMAP also measured expansion rate of the universe of this accuracy, which is kind of impressive because, let's see, 30 years ago, maybe? There's a debate between two prominent scientists arguing whether this was 50 or 100. Now we're talking about 70 plus or minus 1. I mean, that's almost crazy. Age of the universe is determined to be high precision. And like I told you, this came from distance. That's very important, okay? We didn't measure age of anything. We actually measured distance to decoupling epoch and divided that by speed of light. That's why our precision is very good. All right, what did we do, really? So we have these 5 maps of microwave measured in 5 frequencies. We shouldn't forget the fact that we always have galaxy. Okay, we're living in galaxy. It's unavoidable. Galaxies are emitting microwave. Why? For example, Milky Way has magnetic fields. Magnetic fields with electrons. Electrons circling around the magnetic fields. What do? They emit synchrotron. Synchrotron spectrum falls as frequency as 1 over frequency cubed. What that means is if we go to lower frequency, it booms. It's booming signal in the microwave. What you see here is a synchrotron radiation. As you go to higher and higher frequencies, synchrotron diminishes, but then you have another component coming up. Dust. Dust exists in the galaxy. Dust is heated by starlight and re-emits. Emits in microwave also. That's what you see here. Somehow we have to subtract that out. And in between, you have another component called free or Bremsstrahlung. That's the only German word I know at the moment. So you have a proton and electron colliding and emitting free radiation. That is dominating somewhere around here. And then you have cosmic micro background. You have 4 components you have to separate. How many frequencies do you want to have? At least you want to have 4. And we decide to have 5, just in case. Then you separate various components using frequency information. Then that's what you end up having. So you now can clean the galaxy and do the analysis of the microwave background without worrying too much about galaxy. Okay, now how do we do the analysis? Usually what we do is the following. We want to quantify how fluctuating microwave background is depending on the angle on the sky. You take one spot on the sky, you take another spot on the sky separated by some angle theta, then you ask this question. When one location is negative, is the other location negative too? If the answer is yes, you have positive correlation at the separation of theta. If the answer is negative here, positive here, always, then you have positive correlation. Negative correlation. Okay? When you don't have any correlation, when you can't predict the sign of temperature here, regardless of the sign of the fluctuation there will be no correlation. So correlation will be 0. This is what we call two-point correlation function. It's a product of the temperature and isotropy. It's separated by some theta. So it's a quadratic quantity in temperature. But that's good. But usually when we predict things in Fourier space. So it turns out that it's more convenient to do the Fourier transform of this. But since we're dealing with a temperature and isotropy on the sphere, it's more convenient to do spherical harmonic analysis or Legendre transformation. That's that. Then these Legendre coefficients are called power spectrum. This also characterizes how much fluctuation you have as a function of angular scale, but now you have angular wave number instead of angular size, and they are reciprocal of each other. More precisely, L here is 180 degrees divided by theta. Oh yeah, very good. So you ask, for example, what about the orientation, or for example, yeah, very good. So if you multiply these two temperatures together, it's one measurement of fluctuation, but it's highly noisy because you have only one product. So what we do is we assume that the universe is statistically isotropic, meaning when things are separated by the same angle, it doesn't matter if it's this way or that 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 way. So we azimuthally average this correlation. Yeah. And this is what Kobe saw. So Kobe's angular resolution was 7 degrees. So it sort of cuts off at 9 degrees here. L of 20 or so. L of 2 is quadruple. Y sub 180 degrees divided by 2 is 90. 90 meaning, okay, you are divided sky into 4. So hot, cold, cold. That's quadruple. Then octuple and L equals 4, 5, 6, 7, right? Most important fact here is that it's non-zero. So fluctuation is definitely there, right? So this is what gave Kobe team a Nobel Prize. So you have fluctuation here. WMAP went to small angular scales. Then this is what we saw. This is Kobe. Then we have this kind of thing. So what's going on here? That's pretty remarkable. This is the kind of thing that you don't usually find if you are living in the real space. Right? You see? If you Fourier transform this, you see something like this. What's going on here? It turns out that this was already predicted back in 1970s and 1980s. What happens is this. Remember that the universe has a hot soup, like hot miso soup or hot tortilla soup. And then you throw like potatoes or maybe tortillas. then what happens is there will be ripples created, right? That's what the water does. That's what the fluid does. When the universe was very hot, it was the soup. It was a fluid made of protons, helium nuclei, electrons, and photons. Now, when you then perturb the fluid, you create ripples. It's unavoidable. So the fact that the universe was hot and dense, just like a soup, created this beautiful acoustic oscillation. This proves, again, that the universe back then was hot. And something was perturbing the soup. But we can now take advantage of this. Because remember that this soup is made of protons, helium nuclei, electrons, and photons. If you turn the knob and then changed the abundance of helium, abundance of protons, or abundance of dark matter, abundance of photons, they all affect shape of the acoustic oscillation. Right? I don't have time to go into details, but let me just tell you that the ratio of the first to second peak ratio, first to second peak will tell you about the density of helium and hydrogen. Peak ratio of first to third will tell you about total matter density. But interesting thing here is that this peak will tell you about only helium and hydrogen. This peak will tell you total matter, not just helium and hydrogen. So if you see any difference between this and that, right away you know that there's dark matter. Okay? But it's even more interesting than this. It's a peak height ratio that gets you, right? But baryon density is not the dimensionless quantity. So what kind of dimensionless quantity we are measuring here? We're measuring energy density ratio of baryon to photon. But because we know the photon temperature, we can calculate the photon energy density. Because we know the denominator, we can get numerator, which is baryon density. Third peak is very interesting. This actually tells you total matter, including dark matter, to total radiation, including neutrinos. Neutrinos are radiation because they're almost massless. So they behave like radiation. Okay. Therefore, if we fix, for example, things like number of neutrino species, then we fix the denominator and we can learn the numerator, which is total matter density. But if we know about total matter density already, you can constrain number of neutrino species, okay, by doing this measurement. That's interesting. So let's do that then. So third peak, total matter is baryons, helium and hydrogen, plus dark matter. Total radiation includes photons and neutrinos. It turns out that neutrino temperature is slightly colder than photon temperature. All right, let's assume that. Then, given assumed value of the number of neutrino species, at this point actually it doesn't even need to be just neutrinos. It could be any relativistic particles in addition to what we know. Then we can get constraint on number of neutrino species. So that's how it works. There you go. So you have total matter density and then number of effective neutrino species. If you don't add information from other measurements about matter density, you cannot determine number of neutrino species. Yeah? There's a total degeneracy between omega matter density, and the number of neutrino species. But once you add the information about matter density, then you can break the degeneracy and you can measure number of neutrino species. It's 4. Okay. It's not 3. All right, that's interesting. But of course, error bar is like this. So 4 plus minus 1. Okay, so 3 is still consistent with 1 sigma. Accuracy. After this, lot of new data came. And at the moment, it looks like our latest measurement indicates that it's a 4 plus minus 0.5. 1 sigma. So it's 4, not 3, at 2 sigma. Wow, it's interesting. So it's interesting. So Planck will improve this measurement by cutting the error bar by a factor of 5. Yes. Yeah. So very good. So this is the neutrinos or any particles measured at the temperature of 3,000 kelvins. So if the mass of these particles was greater than something like 0.6 eV, they would behave like massive neutrinos, not massless. So that would drop out of the equation. So these particles have to be light. They don't have to be massless, but they have to be much lighter than something like 0.6 eV. EV, yes, very light stuff. Gravitinos could be in there, that's right, yeah. But gravitinos, so thermal gravitinos could be in there, but if you create them non-thermally, then abundance is very different, so it's a different story. Stellar neutrinos could be in there, so. Okay, we can also measure the total mass of neutrinos. So let's assume that there are 3 species of neutrinos. How massive are they? That's a constraint we get. 0.6 eV. What's interesting about this is that this is much better than direct constraints coming from particle physics, such as tritium beta decay. So cosmology has been quite influential in that area too. Okay. All right, so let me switch a gear, and in fact I have to speed up a little bit. Talk about polarization. This is very interesting, okay? So whatever I talk about so far relies on temperature. But cosmic microbackground is weakly polarized. And I'll tell you why. In fact, we even measured polarization directions around hotspot and cold spots. This is something I'm very proud of, so let me just spend some time explaining to you. So how is polarization created? It's no different from classical electrical dynamics, Jackson. Okay? That everybody hates. So you have an electron here. Light is coming. Well, what it does is it oscillates the electron like this, and then electron will emit using dipole, like dipole, then light coming off. But it only does so for only one of the polarization directions, because photon is transverse. If electrons are oscillating like this, then let's see. Yeah, so for example, look at this horizontal mode. By horizontal mode, electron will oscillate horizontally. But then no photon can come to this direction, because that kind of oscillation mode will be longitudinal, not transverse. So only the vertical mode can give you any contribution to the polarization, the scattered light this direction. Yeah? So one scattering, in principle, will create polarization. But in reality, in the things like cosmic microbackground, electron is surrounded by radiation. Photon is not coming from one direction. It's surrounded by all the photons. When the temperature of the photons coming from this direction, temperature of photons coming from that direction are the same, then, after all, synthesized light, scattered light, has no preferred polarization. So no polarization. So what you need to have is first, Thomson scattering, second, anisotropic radiation pattern around an electron. That's what you need. Then you have asymmetry in the vertical and horizontal oscillating modes that will create polarization. So you need that. So after all this, there's one principle that you can take home. You have, let's imagine that you have electron here, and the hot photons are coming from the above and bottom, and cold photons are coming from right and left. They figure out what kind of polarization direction you have. If you think of that a little bit, it turns out that polarization direction is always parallel to hot. Okay, that has nothing to do with cosmology. Has nothing to do with cosmic microbackground. It's just a fact of the electrodynamics, electromagnetism. There you go. Then how does CMB create anisotropy? First of all, there's a matter lumpiness that you saw at the beginning of the movie. So some parts of the universe is over dense, some parts are under dense. Then you have gravitational potential, which is deep when it's over dense. Okay? But then once the photons are at the bottom of the potential well, they have to climb up against potential well. Then they lose energy. So on this scale, gravitational potential well appears as cold spot. Okay. Right? So then, now you can do the polarization. Okay? So you have this plane wave, and you have hot, cold, hot, cold, hot, cold. Polarization is parallel to hot. Draw a line here. Right? Then you get polarization. So parallel, anything in between is the 90-degree rotation of that. That's nice. So that's how you create polarization in cosmic microbackground. It's coming from the lumpiness. There's another way of looking at this thing, namely you have stuff falling into the potential well, and it happens to be that polarization direction is parallel to the direction to which plasma is moving at redshift 1000. That's nice. So using polarization, you can actually get the velocity information of the plasma moving. Okay. So let me just skip these technical details and then get to the results. So, however, polarization is faint It's very, very faint. It's a microkelvin order. WMAP doesn't quite have sensitivity to detect it pixel by pixel basis. When astronomers are put in that kind of situation, there's only one thing that all astronomers would do: stacking. So what that means is, when you don't detect anything in one location or another location, you just add pixels to beat that noise. Now, we have a fairly good argument here. So whenever you see temperature cold spot, hotspots, they correspond to potential wells. Yeah? So what we do is to find all the peaks. Positive peaks, there are 12,000 of them, and cold peaks, there are 12,000 of them also. Actually, this map turns out to be fairly close to Gaussian distribution. So you have almost equal number of hotspots and cold spots here. Then add all the pixels of the polarization data around cold or hot spots. Then you get these images. Now, simulations tell you that we should see this. So around the cold spot, you have radial at 0.6 degrees and tangential at 1.6 degrees. We see that. That's data. And around the hot spot, we see the opposite of sign. So 0.6 degrees, it's tangential, and then 1.2 degrees, that's radial. We see that too. Significance is H sigma. It's a beautiful confirmation of the standard picture. What is a standard picture? Standard picture is when you have gravitational potential well, stuff is falling in, right? So what that means is, what you should be seeing is so-called E-mode polarization. It should be either radial or tangential, but shouldn't be like this vertical thing. It shouldn't be there. Okay? Gravitational potential will never be able to create this. But there's another thing other than gravitational potential that can give you something like this. That's gravitational waves. So if you detect this, then that's a good indication that you have seen gravitational waves influencing cosmic microwave background. Now, how does it work? It works like this. So gravitational waves are coming toward you. What do you do? So gravitational waves stretch space, okay? So let's put particles like a ring. And then let gravitational waves come toward you. Okay, now gravitational waves are really coming toward you. Then it does this. There are two polarization states because gravitons are spin 2. So they have two polarizations, so-called plus mode and cross modes. Now, remember that here, space is stretched. Space is stretched. When space is stretched, there will be a redshift. So photons get colder. So what that means is this. Let's put an electron in the middle. What kind of radiation pattern would electron see? It sees this. It's blue shifted here, so it's hot, and red shift there, so it's cold. Automatically, gravitational wave generates quadrupole. That's exactly what you need for polarization. And the polarization direction is parallel to hot. It's hot here and cold there, so polarization direction would be like this. It automatically generates this. This is completely different way of generating polarization compared to gravitational potential. In fact, you can generate both this and the 45 degree tilted because gravitons have spin 2. That's how you generate B-mode polarization. You otherwise wouldn't generate.
Static gravitational potential, how do you distinguish between wave and potential? In static gravitational potential.
It can be static gravitational potential and can be time-dependent gravitational potential, both of them. Yeah. Then let's talk about this ratio, so-called Tensor-to-scalar Ratio. What does that mean? So we've learned about gravitational potential already. We see them in the cosmic microwave background already. Then let's talk about gravitational wave also, but let's talk about power available in the gravitational potential compared to the power that's available in gravitational potential. We haven't detected gravitational waves yet, so this quantity R, we put an upper limit on this quantity. Cosmic inflation that we'll introduce later will predict, generically speaking, R that's less than 1. to come back to this. Detection of this has a profound implication for theory of inflation. This is the power spectrum, but for polarization, not temperature. Otherwise, it's the same quantity. So CL divided versus multiple L. This is E mode power spectrum. Remember this tangential or radial mode. We have lots of detection here. So E mode from gravitational potential has been measured. But these are all upper limits on the B mode, no detection. Okay? That's a holy grail. Then let's speak about inflation. So inflation is the following ridiculous theory. Okay? It says when universe was very young, universe has expanded with exponential acceleration. It's a fast acceleration. In fact, for example, it takes an atomic radius, and in a tiny fraction of a second, in fact, like 10 to the minus 35 seconds or so, this size becomes solar system size. It's ridiculous. It's ridiculous. Okay, you're ridiculous if you believe this, right? Unless it's actually confirmed by data. If it's confirmed by data, well, that's great. The people who proposed this were genius. That's great. So let's see how it goes. Yeah, but that's okay because it's space that's expanding, not particles that are moving. All right, so it's a cosmic inflation. It's like, so it's here. Dark energy is what's causing the later time acceleration. But early universe acceleration is a cosmic inflation. It's enormous, ginormous acceleration right there. Is that right? Now, nice thing about the inflation is that it actually creates lumpiness. Now, you saw a movie at the beginning, universe was born, expanded, you already saw lumpiness. Where does that come from? In other words, you saw cosmic hot soup, you saw acoustic fluctuations, but until someone dropped tortilla into tortilla soup, there won't be ripples. Somebody had to do it, and who did that? That's the question. That's a big question. And inflation did it. How did it do that? It did that through quantum fluctuations. I think I have a slide later, so let me explain that later. But okay. But anyway, who did that? So let's figure that out. This is WMAP power spectrum again. Now we know what's causing this acoustic oscillation. It's acoustic waves in fluid, which is completely characterized by how much hydrogen we have, how much helium we have, how much dark matter we have, how much neutrinos we have, how much photons we have. Let's get rid of that and see what's the spectrum, what's the spatial fluctuation spectrum of the stones, well, tortillas that were dropped at the beginning of time. That's this. So we get rid of primordial ripples, these oscillations. That's primordial ripples. The power spectrum of primordial fluctuations. It's non-zero. Okay, that's of course important. But another important thing is it's almost scale independent. It's called scale invariant spectrum. Well, but early universe didn't have to do this. Early universe could have done this. You can have more power on larger scales and less power on small scales, or more power on small scales and less power on larger scales. Let's parameterize this by power law. L to ns minus 1. And inflation predicts it should be constant across the multiples. So ns is roughly speaking 1. That's what the inflation predicted. So theory says, cosmic inflation, there were quantum fluctuations. But how much quantum fluctuation do you have per scale depends on how fast inflation proceeded during the inflation period. So inflation may first occur, then get faster and faster, or acceleration may be such that it accelerates, but the acceleration is getting slower and slower. We can actually measure expansion history during inflation using this measurement. That's quite remarkable. Okay, so this is a very powerful method to learn about inflation. By the way, I forgot to say this. Maybe I should say this here. Quantum fluctuations is given by this expansion rate in natural units. Why is it relevant? Expansion rate has a dimension of 1 over time. So if you have less time, quantum fluctuation is bigger. I mean, that's nothing but the Heisenberg's uncertainty principle, right? Or, you know, it's like a bank. If you go to a bank and then ask for $1 to borrow, then they will let you have $1 for, say, a couple of days. Then you come back and return $1. But if you ask them for $1 million, first they will ask you to go to the hospital. But maybe they will do the following. Okay, you ask them, can I borrow $1 million in 1 second? So you borrow money and return, right? But you can do this. So Heisenberg's uncertainty principle tells you that you can borrow energy if you promise to return it in a very small time period. What that means is, early universe, the time that's available, at least standard inflation paradigm postulates that the inflation happened in a tiny fraction of a second like this. Expansion rate, therefore, is enormous. You can borrow enormous amount of energy. How enormous is that? 10 to the 12 GeV. That's enormous. I mean, you can't reach this energy using any kind of accelerators you build today. So this is a nice window that you can use to probe the high energy physics. So inflation does this. First, quantum fluctuations are generated on small scale. The inflation stretches this to macroscopic scales. This is like a very nasty thing, because here you promise to return your energy back to vacuum, but inflation stretches so that enormous that you can't return it anymore. So it's a free meal, right? You just got energy from quantum world and made it classical. But let me be honest with you. How this really happened, how quantum fluctuation became classical, is still unsolved mystery. It looks like it's happening, but we don't really know why so. So that's another avenue of the research. That's difficult, but it's there. So what did we learn? After all this, we actually learned that the measured value of NS that's predicted to be around 1 is not really 1. It's less than 1. In fact, inflation actually liked this result. So I'll come back to that later. But not only does inflation create quantum fluctuations in potential, but they also create quantum fluctuations in gravitational waves. So quantum fluctuations also occur in space-time itself. That's gravitational waves. It's the same story. So, but therefore, detection of B mode polarization, this vertical mode, is important, because that's really the direct way to probe inflation. For example, something like this diagram is helpful. The vertical axis is this Tensor-to-scalar Ratio R. So positive means you have, so okay, 0.1 means you have 10% power in gravitational waves, relative to gravitational waves, relative to gravitational potential. That's R versus NS. And then usually inflation models occupy a small section on the parameter space here. For example, when inflation is driven by scalar field with self-interaction 504, they predict values like this. These are 1 sigma and 2 sigma controls from WMAP. So these points are gone. And that's pretty amazing, because we just ruled out particle physics motivated model of inflation using observations. You're no longer allowed to just come up with arbitrary models. So it's a real science now. Right? That's pretty amazing. Now, let me see. I guess I'm running out of time. Let me just say one more thing. So this is coming, everything I've spoke about relies on 2-point function. And you can do real area universe physics here. You can also use 3-point function. Why 3-point function important? 3-point function is important because 3-point function vanishes for Gaussian fluctuations. Why do we care? Because almost all inflation scenarios predict that the fluctuation should be Gaussian. So you detect this, you rule out a whole suite of inflation models. I will emphasize here, this kind of study already assumes inflation and then selects models of inflation. This approach doesn't assume inflation. It just tries to rule out inflation as a paradigm. Because you have three points, you can come up with all sorts of shapes of the triangles. After many studies, it turns out that this particular shape called the squeeze triangle, where one of the L's, it's K here, one of the L's is much smaller than the other two. If you detect this, there's a theorem saying that all inflation models driven by single scalar field, doesn't rule out multi-field, but single scalar field, will be ruled out altogether if we detect this signal here. This signal is usually, amplitude is usually characterized by parameter called FNL. All single field inflation models will predict FNL 0.02. All of them, okay, regardless of models. Current limit is this, 2 sigma level, so we haven't seen anything. Now, that's good. But interesting thing is, right now, the 1 sigma bound of this is FNL of 32 plus minus 21. And the 9-year data is telling me that like a 38 plus minus 19. Again, it's one of those 2 sigma things, right? It seems like it's positive at 2 sigma level. Planck will cut the error by a factor of 4. So if the central value remains to be 30, it doesn't have to be, but it does, then Planck will see it at 6 sigma level. So that's one parameter you want to pay attention to when Planck satellite delivers data next year. So Planck satellite, okay, let me first summarize. So first of all, cosmic micro background is a fossil light of the Big Bang. We can determine ages and composition and expansion rate and so forth. But now, frontier of this science is the early universe. Next big thing, we want to detect B-mode polarization. Another big thing is the 3-point function as a way of rule out inflation. And then we have this Planck satellite that was launched in 2009. And then, oh, this is too optimistic. It's actually March 2013. Planck has mapped the whole sky already. But Planck is 10 times more sensitive than WMAP, but it's cryogenically cooled mission. It already used up all the helium. So it mapped the sky in 30 months. Now it's gone already. So they have taken all the data they wanted to take. They are furiously analyzing the data. I'm not a part of Planck, but they are expected to deliver the data, the first cosmology results, March 2013. Then we expect to see FNL or not. So if FNL is 30, inflation will be gone, single field inflation will be gone by March 2013. And also, Planck is expected to deliver this exquisite accuracy on the power spectrum. You can't even see error bars here. So that will improve precision on NS. Also, it's expected to do a lot better on the B-mode polarization. If R is 0.1, Planck will see it. So therefore, it is this R, NS, and FNL are the parameters that we want to pay attention to when Planck will announce the results if you're working in early universe physics. I'll stop here. Thank you.
That's great. Thank you, Elichiro. Are there more questions? Peter.
One of the Untitled experiments that continues to titillate D1 among many others, the probably possible challenge to detect cosmology. Has anyone had any ideas to date?
No. But we sort of see it in CMB. So it's an indirect effect of neutrinos on the CMB. That's been detected. But the direct detection of 1.9 Kelvin thermal neutrino background, that's hard. Yeah.
You see the TMB power spectrum is at 2000 Kelvin, right?
Mm-hmm.
Is it possible to see that as the 2000, 1000 Kelvin, and then see the evolution of plasma density or matter density?
Very good. The answer is unfortunately no, but for interesting reason. So here, the CMB was released at the temperature of 3000 Kelvin. Then the question is, can you see things also here, right? No, because this process of recombination, protons capturing electrons, is very fast. So basically, they recombine at once. So universe clears up instantly. If there's a scattering happening here, if there are free electrons here and scattering part of the CMB, then yes, you can do the tomography. You can actually look. You have slices that you can play with. But the fact that the recombination process is so fast implies that you really have only one epoch that you can play with.
I have a question about this picture. The temperature is equivalent to something less than 1 electron volt.
Yes?
The binding energy of the helium is 13 electron volt. So why you say that there is a very sharp?
Very good. Very nice. Yeah. Thank you. So yeah. So the binding energy of hydrogen is 13.6 electron volts. That's 100,000 kelvins, right? Why 3,000? It's so for very interesting reason. It turns out that there are 2 billion photons per 1 proton. So what that means is, even if your temperature is low, you have lots of photons still high energetic enough to ionize neutral hydrogen. So you have to have temperature that's way much below 13.6 electron volt to really terminate the photoionization. So it works out such that this temperature is given by basically 13.6 electron volt divided by log of 2 billion. Then you get this. Yeah.
If you take into account the neutron and lithium,
Yes.
don't you limit the number of other particles?
You do. Yes. Yes. That's right. So for example, it's getting very interesting, by the way. So you have big bang nuclear synthesis, right? Within 3 minutes from the Big Bang, you synthesize helium nuclei, deuterium, lithium, and all that. And all that process depends on baryon density. But also, all of that depends on how fast the universe was expanding back then. And that depends on number of neutrino species. And then from the measurement of helium abundance, which is 0.24, so 24% of the mass in the baryon is in helium. That measurement limited number of neutrino species to be 3. But recent reanalysis of the data indicated that it's 25% rather than 24%. If you believe that, it's 4 neutron species you need. But there are 2 camps now, 24%, 25%, with such a tiny error but that they don't overlap at all. So we don't really know which one is correct. Yeah.
Debate about the lithium set and WMAP.
Oh yeah. So it's completely different issue. That's another thing. So lithium. So okay, if the helium is 24%, then measurement of helium abundance is 24%. Measurement of deuterium abundance, that's 10 to minus 5, and then helium-3, they're all consistent with baryon density being 4.6% of the total energy density. But lithium is off. You have much less lithium than you would expect. But lithium is a measure from the stars that will destroy lithium, so maybe that's the, yeah, that's the, yes. Yes, so here, neutrinos, by the way, when we say 4, 3 are standard ones, so we need only 1 more. What we measure here is the energy density of the total species. It doesn't matter what kind of interaction properties they have. So yes, even if the extra species is completely sterile, we still see them.
Maybe one more question.
How do you determine the center of the universe?
There's no center of the universe. I'm sorry, what do you mean? How do we determine?
Determine the center of the universe. Because you say the way to determine the Big Bang point, I just say use this distance, measure this distance
from the origin of the Big Bang and to the present
So first of all, yeah. So there's no origin of the Big Bang because when universe, there's a universe here, and every point in the universe heats up, right? So there's no center of the Big Bang. Now we, of course, observe things with us at the center, right? Because we observe things like this. So we are, of course, surrounded by our own surface of Big Bang, but that doesn't mean that we are at the center of anything, or center of the observation. But it doesn't mean that there's a center of the universe. Does it make sense?
So when you imagine the distance, so
Yeah.
point you imagine, I mean, we're on the Earth. So you imagine the distance from some point.
Yeah.
And you use this distance divided by the
Right. That's right.
to imagine the edge of the universe. So where is this point?
That's the edge of the observable universe. So light. So because the universe has a finite age, we cannot see the entirety of the universe. We can only see the edge. So we can only see the light that has traveled for 13.7 billion years. So that's the edge. That's the edge we see, right? But yeah. So it doesn't mean that we are really seeing the edge of anything. It just means that these are the photons that were emitted 13.7 billion years ago.
When you said point, you mean it's the surface of radius r, which is that distance.
Right. Yeah. We're surrounded by this
For the
surface.
sake of time, I'm going to cut it off, but Elichiro is here all day tomorrow, so if you'd like to talk to him, let me know, and we'll track him down for you. Thank you again.
Thank you.